So we've already looked at what an inequality is on the front page. We've already done one example of a polynomial inequality and one example of a rational inequality. So now this video is just in case you need some extra help completing examples 3 and 4 and the application problems about inequalities, either after you take the retake or just in class. So here's my rational expression. I've got 0 on this side. So where would the zeros occur? So remember we said wherever there are x-intercepts and wherever there are vertical asymptotes. So I'm going to look for my x-intercepts first. This factors into what? X plus 3 times x minus 2. So my x-intercepts are at -3 and +2. And my vertical asymptote is at x equals 0. So I have 3 critical values. So those are my critical values. So I'm going to determine my test intervals. I'm going to use open circles on my number line because it's strictly greater than 0. So I've got -3, 0, and +2. So I want to see what's going to happen to my function on either side of these. So I'm going to plug -4 in to my original inequality. I'm going to plug in -1, +1, and +3. So those are on either side of my test intervals. So all I really care about is if my function, when I evaluate it, comes out positive, greater than 0. So I'm going to evaluate each of these. You could do it by hand. I'm going to just plug it into my graphing calculator. So if I've got x squared plus x minus 6, and I'm dividing by just x, I'm just plugging this into my y equals menu, and then I'll be able to see where in my table, so I'm going to start my table at -5 and count by 1. So let's see, in my table I am negative over here. I want to be positive based on my inequality, so I don't want to include that region. When I look between -3 and 0, I've got positive numbers, so I want to include that region because I want greater than 0. When I keep going beyond 1, I get a negative value, -4. When I keep going beyond 2, I get positive values. So my two solution regions are when x is between -3 and 0, or when x is greater than +2. And I just want to show you on the graph what my function looks like. So remember, we wanted the graph to be above the x-axis, greater than 0. So here it's greater than 0, and beyond 2 it's greater than 0. So it looks like I've captured the correct regions of the graph. All right, so example 4, I cannot evaluate this rational inequality until I have 0 on one side of the inequality. So first I'm going to use common denominators to rewrite this as one rational function. So I'm actually going to subtract this fraction to the other side. So 4 over x plus 5 minus 1 over 2x plus 3 is greater than 0. My common denominator is going to be both of these factors, x plus 5 times 2x plus 3. So I'm going to multiply by 2x plus 3 in the numerator and denominator, and I'm going to multiply by x plus 5 in the numerator and the denominator. So my new rational inequality, my denominator, I'm just going to leave in factored form. So I've got 2x plus 3, x plus 5. In the numerator, I have to do some simplifying. So let's see, I would have 4 times 2x is 8x minus 1x, right? 1 times x. So 8x minus 1x is 7x. And then here, 3 times 4 is 12. And then here, minus 1 times 5. So I'm doing 12 minus 5 would be 7. So 7x plus 7 is my numerator. So where are the zeros and the vertical asymptotes? Where is the 0 for the numerator? If I plug in -1 for x, right, because this is really 7 times x plus 1. So -1 is my 0. Where are my vertical asymptotes? -3/2 for this one, and -5 for this one. And I'm going to plot them on the number line, all with open circles again. So open circle at -5, open circle at -3/2, open circle at -1. So I want to look at -6, -2, -1.25, and maybe 0. So you could either plug in the original inequality or your new inequality. I'm going to plug in my new inequality into my y equals. So 7x plus 7 divided by, I'm going to do 2 parentheses, 2x plus 3 times x plus 5, 2 parentheses. Go to my table. I'm going to go all the way down to -6. -6. But I'm going to count by 0.25. So second table. So at -6, my answer is negative, and I want it to be positive, it looks like. So no for -6. At -2, if I scroll up, oops, sorry, they're all positive, right? So check. What about at -1.25? So if I go to -1.25, oh, I get negative again. So don't want that little region. And if I go above 0, I get positive values. Check. So my two solution regions were between -5 and -3/2, and x has to be greater than -1. So let's look at the graph of this rational function. Where is this rational function positive? Here's that region, -5 to -3/2, and then here's kind of that other region. It's up here and it dips and it's like really close to 0. So anything greater than -1, it pops above the x-axis, it looks like. So I got that correct. So now we're going to look at a couple application problems. So the business application for cost, revenue, and profit. So here's revenue, here's cost. They're both measured in dollars. X represents the number of units sold. How many units must be sold to obtain a profit of at least $750,000, and what is the price per unit? So profit is your revenue minus your cost. So I'm going to do this one using the graphing calculator. So I'm going to put revenue minus cost in my y equals menu. So x times 75 minus 0.0005x, close parentheses, minus parentheses 30x plus 250,000, close parentheses. What do I want that to be above? $750,000. I'm actually going to enter $750,000 as my horizontal line for Y2. Now I need to adjust my window. So I want to be able to see maybe an X or a Y maximum of like $1 million maybe. Right? It's going to be above 750,000. So $1 million is above that. How many units do you think we have to sell? You want to sell 20,000 units? I have no idea. Might have to go higher than that. I don't know. Let's look at the graph and see if we can see. Oh, I guess I can see it. Oh, but I didn't look over far enough. I want to see where this blue line gets above the red line. So I'm going to go back to my window. How about we also do 100, or we do 1 million, I mean, products. Okay, so 1 million for my X max. So now I'm too far out. So there's my little tiny blip above 750,000. looks like I have to get a little bit closer. So I'm going to go back to my window. I'm going to do 500,000 and see if I can get closer. Okay, so here's my parabola. I want to know where I'm above that. So I want to know where those two lines are intersecting each other. So the way to do that is go to second, above trace is the word calculate, intersect. So I'm on the first curve somewhere, I'm on the red curve somewhere. So I'm going to go really close to this first intersection point over here, so on the right hand side. So they intersect at 50,000 units. So I'm just going to write down 50,000 units. And let's see where they intersect on this other side. And actually, I could get a closer view if I do a y minimum of, let's say, 500,000. Maybe this will zoom in so we can see it a little bit better where it's intersecting. All right, not much better, but so I'm going to go to second calculate again, intersect. First curve is blue, second curve is red. So here's my second curve, red, and here's my guess this time. I'm going to guess kind of that left-hand side. It intersects at 40,000. So the top of that parabola is when x is more than 40,000 units, but less than 50,000 units. And it says, what is the revenue? So we'd have to know something about the business world and how equations are written, but this sneaky 75 right here is the price per unit. Not that you would have to know that, but just being able to find an intersection point on a graph of where is one function higher than the other function, I think is important. Question number 2, the cost in millions of dollars for the federal government to seize a certain percentage of illegal drugs as it enters the country is given by this function. P is your percent, and when you plug in 25%, they want you to plug in the number 25. So find the cost of seizing 25, 50, 75, and 100% of the drug. So I think you can go ahead and plug those values in. So for example, plug in 25, see what you get. Plug in 50, see what you get. Make sure you put parentheses in the denominator. I think you can do number 2. And number 3, the amount of carbon dioxide uptake in milligrams per square decimeter per hour at optimal temperature with a natural supply of CO2 is approximated by this model. So X is the light intensity. Determine the limiting amount of CO2 uptake. So you're looking for the horizontal asymptote, right? What's the maximum carbon dioxide uptake, which is basically when X is really, really big, right? What is going to be the asymptote? X is the light intensity. What's the limiting amount? So what's the maximum CO2 uptake per hour? So you're going to look at a graph or think about the asymptotes for this one, and I think you can finish that one. And then you can wait, because this review sheet is what we're going to be working on Thursday. So you're going to skip back to 0, 20, and 21 when you're finished with this.